here with 9.Connects. Thank you very much for joining us here today. So we're going to start our webinar here on the layer stackup. So we're going to begin here. And before we go into anything else, we are going to start off with our expectations. And of course, this webinar cannot possibly cover the entire topic in 1 hour. I was thinking about this the other day. I remember taking the CID class and having to spend really several weeks preparing for it. And there's a 3-day workshop before you actually take the CID. And even the 3-day workshop is basically feeding you from a fire hose. And then, of course, there's the CID Plus as well, which is another 2 days of drinking from the fire hose. So the topic of the stack-up may sound relatively simple, but it's actually a very, very complex subject. And we're only going to kind of skim the surface today, but hopefully give you enough information so we can possibly make you dangerous. So because we can only cover so much of the topic in 1 hour, obviously you want to seek guidance from your contract manufacturer, your fab house, your assembly house. And of course, if you have any experienced engineers at your company who've been there, done that, once burned, twice shy, engineers who've experienced the pleasures and pitfalls of dealing with fabricators and assemblers, you certainly want to talk to them as well. Experience is key in this particular industry. And of course, you can contact us here at 9.Connects. So just to let you know, we are into DFM services, so design for manufacturing services. If you're doing a prototype board and you're having a struggle trying to get it into some type of volume production, we can certainly assist you with that. One of the other things that we've been doing as of late for our customers, we've been getting into test and even on system level design as of late, and we've also been serving our customers as a single point of contact for contract manufacturing. Now, if you also are looking for a contract manufacturer, we know several of them out there as well. So this is an area we know rather well. In addition to that, I'm going to be using a tool from In-Circuit Design. You can see that over here. It is a stack-up planner and a PDN planner. I'm not going to get into the PDN planner today. I am not going to necessarily demonstrate the tool in all of its functionality. However, I am going to use this tool as a talk about layer stackup. So you'll see me pop it up as we're going through this webinar. Reading materials, there's a ton of it out there. Of course, the ones that you want to be most familiar with are those from the IPC. IEEE also kind of dabbles in that area, though it tends to be more on the design side of things. There's several other institutes as well that are very specific to PCB design that you may want to take a look at. Tons of material out there, and that's the problem, is that there's a ton of material out there, and it's just a matter of trying to get through that and understand it. All right, let's get on to the good stuff, shall we? And what we got here is, what is the purpose of the stack-up? Well, first and foremost, the whole idea of the stack-up is to provide fabrication information about the board to the manufacturer. And I think we tend to forget that. We just feel that the stack-up is one of many things that we're doing. We focus so much on the layout that we're not really worried about the stack-up. But the layout and everything else we do with it is wholly part of the stack-up itself. And as I mentioned, I think I've mentioned this time past, but I've seen this happen so many times it bears repeating. And that is that what I've seen very often is that a design always comes out of the chute, guns ablaze, and everybody's moving forward. It seems like there's a rapid development. And then just as you get to fabrication, the wheels fall off the bus and there's a crash and burn. Well, what happened? Well, the problem is that up to that point in time, everything was in theory. You were working on a computer. You were doing simulations. You weren't dealing with physical material. But when you start getting to fabrication, you are now dealing with the physical world. And really what you're doing in a layout design is you are providing instructions for a bunch of equipment to build this real thing. And it's kind of weird because we're never really taught that, especially as electrical engineers. You say, the other guy will take care of it. But with the industry changing the way it is, no, that's our responsibility now. We are actually not just designing a circuit. We're not just doing a layout. We're actually fabricating something. We are manufacturing something. In addition to that, we are also trying to control the impedance, and I'll spend a lot more time on this here because I think this is really important to understand. So obviously, Eric Bogatin reminds us, it's a book that he wrote. He's an MIT professor, and he always reminds us in his book that there are people who deal with high-speed design issues and people who don't know that they have high-speed design issues. The fact of the matter is all of us are going to, if we're not already dealing with it, we're going to have them soon enough. Well, why is that? Well, obviously, the frequencies of the clocks are going much, much faster. But also, the signal times are decreasing quite a bit as well. And if you take a look at this particular picture that I've got over here, this explains why. What we have here is a transient analysis. We're familiar with transient analysis. It's basically a wave. In this case, it's a square wave, which we associate with it being a digital wave. What we tend to forget is that square wave is not in nature, it's not natural in nature. It's actually what they call a synthetic wave. And that wave is made of a summing of numerous frequencies. And that's what you see here with the Fourier analysis, is that if you take this sine wave and you look at it from both the voltage perspective and the frequency perspective, these are all of the frequencies that are made up and summed together to make that square wave. And you can see that it goes well into the gigahertz. So the rise times, because of the silicon getting much smaller, the rise times are getting much faster. And as a result of that, even though you're using a 10 megahertz clock, and maybe the setup time and whatever else you may have over there works well within the 10 megahertz clock, that rising edge may actually be putting a lot of frequency onto your line and actually causing noise and signal integrity issues. So we really do have to control the impedance. It doesn't go away. We have to control it. So how do we do that? Well, first and foremost, let's spend a few moments to talk about impedance itself, just kind of a quick refresher. It's made of resistance and reactance, and its units are in ohms. Now, most of us like the resistance part of it because it's constant. Regardless of the frequency, it's always going to remain the same. It's the reactance part that kind of gets us kind of tripped up. So let's take a brief look at that. Just keep in mind that the reactance is what they call the imaginary part of the impedance. I always got a kick out of that name, imaginary, because it's very real. There's something very real happening with the signal over here, so I don't know how I can possibly imagine it. But the mathematicians call it imaginary, so we'll kind of have to stick with that. But really what's happening over here with the reactance is as follows. We're dealing with a capacitor, okay? Or the capacitor end of things, what happens, we create electric fields. And by the way, we're going to see this over and over again throughout the entire stack-up, because if we really look at a board stack-up, it's basically a series of capacitors. And when, you know, if it's DC, it's one thing, but we don't work in DC. We work in signals. So signals are going up and down, which means the electric fields are changing. And when the electric field changes, or pardon me, when the voltage changes, the electric fields change. And because things are charging and discharging in a capacitor, we get a reactance to the voltage. And in a very similar fashion, we have things going on with the inductors. So we have magnetic fields that are going on. And so, of course, as the voltage is changing, there's a ratio with the current, and the current's now changing, okay? And so what's happening is the magnetic fields are changing, so we have a reactant to the current. And you can see these relationships here. They're always 90 degrees off, or for the most part 90 degrees off. There could be some other factors in there. But the capacitor, the voltage always leads the current by 90 degrees, and for the inductor, the current leads the voltage by 90 degrees. So I guess the question is, why do we care? Because if we look at the mathematics over here, you'll see the three equations for basically impedance. Well, the resistor one is easy. It's a constant. We wish everything was a constant, but unfortunately it doesn't work that way. But what you see over here is when you look at the capacitance and the inductance, we have this little thing called omega. So forget about the J. That's the imaginary thing we throw in there just to represent the imaginary part. And the C part over here is a constant as well. It's the omega that throws us off, because within omega, this is 2 pi f. Now, the 2 is constant. The pi pretty much could be constant depending on how many decimal places you want to go out. But for the most part, it's constant. But the frequency is constantly changing. And because the frequency is constantly changing, that actually changes the impedance. Okay? So we have to be able to deal with that. All right? So how do we deal with that? Well, interestingly enough, when we're dealing with impedance, obviously routing has a huge thing, let's say call it a thing. It has a huge thing to do with it. But before we even get to the routing, we have to have the infrastructure in place to control the impedance. And when we look at the impedance equation, one of the things you don't see in this equation is length. Okay, that length does have an issue with antennas, and we talked about that in other webinars. However, when you look at the impedance calculation, it has to do with several other things that are very, very specific to your board. What do we mean by that? Well, one of the things is the trace width. Okay. The other one is the trace to plane distance. So in high-speed design, you always want to have some plane that the signal plane or the signal layer can reference. You also have to deal with trace height, also known as copper weight, and we'll talk about this later on. And then you also have a dielectric constant as well. So when you look at this equation over here, it seems like it's heavily controlled, if not almost entirely controlled, by our layer stack-up. And that's why this is so important for us to address immediately and not at the end of the process. The problem that most of us have, especially if we come from what I'll call the old school, and we're using FR4, and we'll talk about FR4 in a couple of minutes. The point I want to make there is that in the past, since we're using FR4 and we knew it so well and we weren't worried about high-speed issues or impedances, if we were starting off with a 2-layer board, we're trying to make it fit, and if it didn't work, okay, throw on another 2 layers. You do everything in symmetry. So we'll go to a 4-layer board. For a 4-layer board, let's go to a 6-layer board. We just kind of shrugged our shoulders, and everything was fine. But unfortunately, we can't do that when we're trying to deal with impedance and high-speed design over here. The trace width and the trace height, which ultimately becomes a part of our rule set, is very heavily influenced, if not completely influenced, by not only the impedance that we need, but the stack-up that we are using. Okay? And that's what I want to give you an example of here right now. So I'll put that one back up here in just a moment. So let's bring this up over here. So this is the ICD Stack of Planner. I already had it running in the background. You don't need to have Altium Designer to run it, by the way. It is a standalone program. When you open it up, you already see a couple of layer examples over here. All right, so here's a bunch of different layers that they're providing for you. But what I'm going to do here is I'm just going to quickly copy one of these layers, so if we make a mess of it, we don't have to worry about it, because I may use it again for another example or during Q&A. So I'm going to go here and I'm going to copy this. I'm going to click on here. We'll create a new one. I'll just call it webinar. Okay, and I'm going to dump this in here. So let's do a paste. So now we've got this. Now, why did I do this? Not to really demonstrate the tool. The reason I want to do this is I want to show you what happens when we start playing with the numbers over here. So here's the characteristic impedance for this layer. And you'll notice that the characteristic impedance on the top and on the bottom is slightly different from the one in the middle. Okay? Same thing for the differential pair as well. Why is that? Why is that happening? Well, the reason why it's happening is for really 2 reasons. Number one, when you look at the signal that's on the top over here, it's only being influenced by one plane. In addition to it, it's also being influenced by 2 different materials. There's a prepreg material and there's a solder mask material. And the same thing's happening on the bottom as well. Where in the middle over here, we're seeing an influence of not only 2 planes, we're also possibly even seeing the influence of the other signal layer, but you're seeing 2 planes over here, and all of it's immersed in the prepreg. So that's why you're seeing different calculations. So there's a built-in field solver in this, so when you make changes, it actually changes these things in real time. So we can play with these numbers all day long, and we can try to get these as close as possible to the desired impedance we want. Now, you'll also notice something here as well, that the characteristic impedance is about 53, 54. Okay, and if you look at these other layers here as well, if we click on layer 8, for example, you'll see that they're a little bit better. As you get a little bit bigger over here, they might get a little better. But the point I'm trying to make here is notice that they're not 50.00 ohms. Okay, or that the edge-coupled one, which is supposed to be about basically 100, is not 100.00 ohms. You can try mess with these variables all day long and get it to show 50.00. But the problem is that you got to understand that fabrication, in manufacturing, there are tolerances that you're dealing with. So even if you got this thing to look pristine at 50, you're kind of wasting your time. You want to get in the ballpark, okay, but there's going to be tolerances there. So you got to remember that no 2 materials are ever made the exact same way. No 2 processes are done the exact same way. No 2 people work the same way. No 2 fabrication companies work the same way. So as a result of that, you're going to get close to 50, but you're not going to get it on the nose. Now, could that change in the future with better technologies? I think it will, but we just got to work with what we got here today and just recognize that, yeah, we want to get this close to 50 if that's what we need, but we're not going to get it on the nose, and we shouldn't try to get it on the nose because the manufacturing process is going to have its tolerances to deal with. Now, one of the other things I want to show here too is, yes, you can play with these things. So for example, if I change the trace width here and I change this, hey, I don't like 12, that seems like that's really large. What if I give this 6 over here? Well, it instantly changes this and it really throws it off. So that's, again, why I want you to be very careful about the fact that in tools, especially like Altium, where you go into the rule set and you say, well, I got my stack up and I'm going to change a width because the manufacturer, because I just want to use this width, the manufacturer should be able to handle it. That's really dangerous because right now you've got a characteristic impedance for both single and differential pair that's way off. And if you did all the routing with six mils and you sent this off to the fabricator and said, sorry, this isn't going to work, you're going to have to tear out that routing and you're going to have to do it based on these rules here. What's the kicker about this is that if you look at the impedances, we already know what the impedance is. We look at the impedance calculation to find Z, but we already know Z. Really what we're trying to find is the trace width and the trace clearance. So that's what we need to do here. All right, so one of the other features of the tool which I do like, and it's something they recently added based on customer feedback, and I'm just going to click on this because it's really useful, is these things called the impedance plots. Why? Because who wants to futz with these things all day long? So if I actually wanted to have an edge-coupled differential pair impedance of 90 ohms, which you need for USB. Do I want to play with this all day? The answer is no. So what the designer did, he went in here and said, you know what, let's make something available here. So based on the information we have, we can actually look at different factors over here, adjust it, and it will get us much closer to it. So we have things like trace width. So here's the impedances, and here are the widths that you would use in order to get those down there. The trace thickness, which, by the way, you'll notice really doesn't have a huge impact on the impedance itself. The trace clearance, and then even for differential coupling, they put two things. They overlay these on each other. So not only the dielectric thickness, but also the clearance as well. Be careful about changing the dielectric thicknesses, and in particular the dielectric itself, because now you're moving away from FR4. You're getting into exotic materials, and you better talk to your fabricator about that. And I'll talk more about that as we get to it. But the idea over here is for trace clearance, for example, if I want 90 ohms, okay, then I just put my cursor over here and I follow it along, and it looks like 8 mils will probably do the trick. So if I, and by the way, I can leave this up here. I don't have to close it. It's not a locked dialog. So if I go over here to the trace width, for example, and I say, okay, I'm going to put this over here to, double-click into it first, get this over to 8, then, no, sorry, that's trace clearance. Let's undo that one here. It was trace clearance. That's why it jumped up. So let's go over here to, pardon me for a second. It was at 12. There it is. I can look at the bottom one here. And then we'll go over here to trace clearance and make this one an 8 here. Then you'll see it jump down to about 88.19. Again, it's a ballpark figure, but this gets me to 90 ohms and exactly what I want. By the way, it didn't have really a huge influence on the single one as well, which is a good thing as well, because this is already where I want it. So just to give you an idea or flavor how to work that. All right, let's push this off to the side here for now and get my presentation back up over here. So we will continue on from the current slide. All right. Materials. So a lot of times a lot of people don't understand the materials that go into a layer stack up. So let's spend some time on this. There's 3 main materials, and actually that's a little bit of a it's a lie. It's 4 main materials. What I didn't add in here is the solder mask. Okay, but for trying to get this thing through the core part of its fabrication, these are the 3 main materials that you're going to need to get everything to kind of stick together. So the first one is this thing called core. I'll talk more about this in a moment. But basically, you can look at it as copper being on top of and bottom of a dielectric. And it is cured material. What they mean by cured material is it's hardened material. So if this is being applied with heat and pressure, because that's what we're going to do, is we're going to laminate these things together over here, you would not expect this core to really become soft and mushy, unlike the Prepreg. And the Prepreg is basically a dielectric material. In fact, it can be the same type of material that's used in the core. It's just, however, it's a partially cured material. Now, the easiest way to think of Prepreg is if you ever had a glue stick and a glue gun, and before you put plug in the glue gun and stick in the glue stick and turn it into a gooey mess, you hold it and it's basically a rod basically a stretchy material, but it's not sticking all over you at that point. It's only until you apply a heat that that's ultimately going to turn into a glue. Okay, so think of the Prepreg in that type of manner. Then you also have a copper foil, and the copper foil is just copper that you would lay on top of the Prepreg, and we'll see an example of this as we move along. So for the core material, I just kind of basically explained it. One of the things that you'll see is that if you look up a particular material, let's say on a Sola or on, let's see, 3M also makes stuff, Rogers makes stuff. There's a number of different companies that make these materials. If you look up FR4, you're going to find dozens of different materials out there, and many of them have to do with the different sizes and weights. So the different, when I talk about size, I'm talking about thicknesses. So different thicknesses of the Prepreg, or pardon me, in this case, the core, and also the top and the bottom copper as well. So when you look at it, you'll see a bunch of these things being listed. The thickness of the material, obviously, it's a copper thickness, and we'll talk about copper weight in a few moments, and of course the dielectric material itself. Thickness does play a big role in things, and you'll see why here in a few moments. But for now, let's talk about the stuff called FR4. It's a material that's been around for decades, and pretty much all fabricators are geared for it. It's just a material that they're always going to default to when you need something done, unless you start saying, look, I've got a high-speed design, and we've got to have different trace widths, and then they're going to start looking at other materials at that point in time. But FR4 has always been the classic material because its mechanical strength is really good. If you ever try to take a printed circuit board and try to snap it in your hands, that's a tough thing to do unless it's a really thin board because it's got great mechanical strength. it does not really absorb water, practically no water, so it can be used in very humid environments. It can be used in marine environments as well. The FR actually stands for flame retardant. I always actually thought it stood for fiberglass resin, but it's actually flame retardant, which means that if a component does blow up on you on your board, the board will not catch on fire. It'll probably melt and it'll smell rather bad, but it will not catch on fire. The component might catch on fire, but not the board. So my recommendation, as we used to joke, don't let the smoke out of the component. The dielectric constant dissipation factors are kind of high, and I'll talk about why this is a concern here in just a moment. So let's jump over to this slide here. So because the dielectric constant is kind of high, it slows down the propagation of the signal, which is completely contrary to what we're trying to do in high-speed design. Okay? So normally you want to try to find a material that has a lower dielectric constant. Now, air has a dielectric constant of 1, so other than trying to use air, if you're going to use any other type of material, you can probably get it down into the low 3s. But just understand here that the dielectric constant of FR4 can be kind of high, and that is impacting the propagation of the signal. What I don't have time to show you today are all the equations that lead up to that. That's about a 15-minute explanation. In addition to that, you have this concept called the dissipation factor, and this is basically a dampening effect. Again, there's a bunch of equations that you'd use to show how this happens, but the easiest way to understand this is that, for example, if you're talking to a very large audience and you're not using a microphone, your voice is only going to carry so far. Well, that's the same thing with high-speed design, is that with a dissipation factor of your dielectric from the FR4, it's only going to travel so far, or you're going to have your signal rapidly dampened, and it's not going to be strong by the time it gets to point B. So that's what I want to say about that. If you're more interested about this and get specifics into it, definitely take a look at this. And I list all of these at the end. This is by a Barry old, I do pronounce it wrong sometimes, and I apologize, Barry. It's only. And Barry here is the one who did create the ICD tool that you just saw here, and he's very deep into these. He's got over 30 years experience. He's written a number of different articles on this, and this is one of them that he's written. So if you're interested in material selection, take a look at this. And one thing I love about Barry is that he writes things that you can read and you understand. You don't have to whip out your differential equations book or your calculus book. He really puts things in a very easy-to-read perspective based on what's out there. So take a look at that. These other materials that are out there, so you want to get rid of FR4, that's fine. But there's other materials out there. The problem with these other materials, they may have great things like better loss dissipation, or they may have better dielectric constant. However, they have other issues. They have their trade-offs with it. And I make the analogy over here to wheat products. So FR4 to me is kind of the equivalent to wheat flour in the baking industry. Say, wow, where did you come up with that? Well, unfortunately, both my son and I have certain allergies or sensitivities to wheat, so I started looking for other products that didn't use wheat. And you found out that all these other flours out there may have one quality that's better than wheat, but they have a lot of other things that don't make the product very useful for commercial use. Wheat bakes very well, it's light, has a decent taste to it, it's very stretchy and malleable, whereas a lot of these other ones may have a better taste, but it's not malleable, or it's very malleable, but it's almost too malleable. It's actually too stretchy, and it's almost like chewing on rubber cement. So with FR4, for example, if you can't use it, a lot of times you want to substitute in other materials, but what you generally find on the PCB side of things is you mix and match materials. You don't just say, oh, I'm going to use this one from Isola, and this is the only one I'm going to use because you're going to probably have some problems with it, whereas you actually mix and match these materials so you compensate for those things that become problematic. And that's the same thing which actually happened in the baking industry. With all this gluten-free stuff, if you really look at the ingredients now, you've got 4 or 5 different flours they're mixing up. So whatever is a deficiency for one flour, it's made up with the other. So hopefully you get the idea of the analogy I'm trying to put over here. But things like absorb the water. Some of these materials that they have out there are very brittle, so you don't want to have, if you're building a board that's supposed to be going into an aircraft, you probably don't want to put it in there. Shake and bake is going to be an issue. Stuff that's too soft. I remember an example about a year ago, IPC, there was an IPC meeting in San Diego, and someone was saying that one particular customer found this really great material with a very low dielectric constant. They made an 8-layer board out of it, and they brought it to the fabricator, and the fabricator turned around and said, after 4 layers, it is so mushy, we cannot register it. after that. So they had to actually go back, change up the materials, which in turn required them to change up the design rules, which in turn required them to change the routing. Okay? Some of the stuff is really brutal to drill, so some of the materials are very, very hard, so you can drill it, but now you're going to pay additional tooling costs because now they got to go through more drills. There's also a little bit of a slippage. Some of the stuff is really slick, right? It's got a very, very, call like an enamel coating on it. It's a very smooth coating on it, so there's a little bit of slippage on the drill when it's first trying to penetrate into the material, so you may not be on target as much as you want to be. And of course, temperature is also affected. So it may have gone through fabrication without any problems whatsoever, but when you got it to assembly over there, it just became a mess. They can't get the components on it, or they have to actually hand solder it because their equipment can't handle it. So be very, very careful of other materials here. Just one other thing I was going to show here, and let's see if I can do this without popping down the whole thing. I can't, so I'm going to escape out here. Maybe I can. There we go. I want to leave this up, and then I'm going to bring back our ICD tool here. So one of the things that they've got with this tool here as well, which is really nice because you're probably asking yourself, I don't even know where these materials are. Where do I get them? What companies are making these things? So one thing that was added with this is actually a library of these things. Now, it's a good thing and it's a bad thing. It's kind of leaving you a lot of rope to hang yourself, as the old expression goes, because all this information's in there. But again, you want to talk to your fabricator so that you don't make the mistake of accidentally picking materials that just aren't going to work, or they're very rare materials or very costly materials. So for example, if I right-click on here on this core dielectric here, I can go into Edit Dielectric, and it's going to bring up this library of information. So it's got information on the core, it's got information on the prepreg, and it's also got information on the solder mask. So the idea behind this is that if you're coming up with your stack up, you can find these materials, you can export this information out to your fabricator, have them take a look, and then they can provide feedback to you if this is possible. They may even provide other recommendations as well. So here's the core materials over here, and I can do a search on it. So if you're kind of curious about FR4, so we'll type in FR4, and it's doing the search in real time, so that's why it's taking a little bit here as it's going through it. Okay, and it's going to find quite a few things out there. And you'll see that there's an amazing number of different FR4 materials out there. There's some from Isola, and I think there's other companies that do it too. Well, in this case, only Isola is doing them. But you also notice there's different resin percentages. The key things that you'd be looking for is definitely the thicknesses of these. And of course, if you are concerned about the dielectrics, some of the dielectrics you can get down a little bit below 4, which is fine as well. And of course, with this tool over here, if there's one that you really like, you just double-click into it, and it puts it in there so that that information is bundled up with the stack up. But that's the idea behind it. So it's a really great little tool, and they've got a nice little library here. If you don't have this set up over here and you just want to browse it, you click on this, and it will bring up the library. Anyways, let's move this on here to some other stuff. Materials. So materials are, in particular, the copper height. This always confused me because the copper height is always told in copper weight. What I find amazing about this is that though the world seems to despise the imperial system, when it comes to copper weight or copper height, it always talks about 1 ounce of copper spread over 1 square foot. So that sounds rather imperial to me in terms of its measurements. So the resulting height of that is that if you take this 1 ounce of copper and you spread it over 1 square foot, you get a resulting height of 1.37 mils. And of course, if you do want to see it in the metric system, here it is in millimeters, and it's equivalent to approximately 35 microns. Now, can you change the amount of copper, the copper height, which in turn would mean a larger ounce of copper? The answer is certainly yes. You'd see that in the listing over there. Just kind of keep in mind how things are working, though. So more copper over here, you should be able to justify or see why you want to have additional copper. What happens here is that, remember, you're working with copper sheets. You put an etch resist on the top of it, and then you put this in a chemical bath, which in turn etches away at anything that is not underneath the etch resist. And of course, that chemical does find its way underneath the etch resist as time goes on. So the thicker the copper is, the longer it's got to be in there, and the more interesting the shapes tend to be in terms of what you get as a result of a trace. Unfortunately, there's never a perfect trace, though. I'm seeing some stuff like from companies like eSurfaces where the additive measures, it's amazing how square those traces look. But for the most part, what we're doing, it's a subtractive process. It's a little bit of give and take. You just got to understand the chemistry behind it. It's not going to be perfect, and so therefore you're not going to get a perfect square here In fact, you're not even sure what you're going to get. It could be a trapezoidal. It could be an upside-down trapezoidal. It could be even a pyramidal shape. It could even look like a square. It could have weird indents over here where it actually ate up in the middle instead of on the top or on the bottom. So it's a little bit of a potluck as to what you're going to get there, but generally they can control that to a very high degree. All right. In terms of material stack-ups and thickness, we talked about thickness for a moment. Let's get back to that here again. The magic number is this weird number called 63 mils. And like, where did this come from? Well, the story behind this is very similar to the U.S. railroad gauge of 4 feet 8.5 inches, which ultimately was traced back to the Roman Empire with the chariots. Okay. Now, in this particular instance, it has to do with a material called Bakelite. And Bakelite is kind of interesting because we never hear of it now, but really for the first half of the 20th century, it was used in a ton of products. And it was first brought out in about 1909 and kind of faded out of the scene in the 1950s and 1960s as new materials came about. And in fact, what you can see is in the 1930s, they were using it for a lot of what I'll call parlor games. So you can see that even billiards were made out of it. There's a picture of it right here. Early appliances were made out of it. Telephones were used with it. Radios, they made radios with it. So if you ever come across a Bakelite, a radio that's got Bakelite on, it's actually considered to be quite an antique to collect. And in addition to that, when the electrical industry was converting from vacuum tubes into transistors, it made its kind of made its debut, because at this point they needed to make something like a breadboard that they could feed it through. And most of the lab benches used a Bakelite/plywood material. And so the lumber industry basically came up with this stuff where you could buy a piece of plywood, and the last ply of the plywood was Bakelite, which had to be 63 mils because they didn't want the plywood to be any thicker than a normal piece of plywood. So we actually got, in our PCB industry over here, actually got this thickness from the lumber industry of all things. Okay, so they saw that these desktops were great, they were sturdy, they're great insulators, and they said, hey, let's just get a sheet of this Bakelite, and that's what they did. And the Bakelite was in 63 mil thicknesses. And ultimately, it even found itself into the connector standards as well when they started doing board edge connectors, because obviously if the Bakelite was 63 mils and you're trying to make a board edge connector, the connector had to accept a 63 mil width slot. So that's how it all kind of got pulled in together. Now, for today's fabrication equipment, though it has been geared for 63 mils, you don't have to build it to 63 mils. The rule of thumb now is that you want 63 mil thickness based on 1 square foot of printed circuit board. So if you have a printed circuit board that's much smaller than a square foot, okay, then you don't have to necessarily go to 63 mils, but you got to keep in mind you got to have some thickness in there because you need some type of reinforcement. Otherwise, it's just going to fall apart. It's going to become very brittle. And in similar fashion, if you've got something like a big heavy backplane that's 2 feet long, then obviously you want to have something that's larger than 63 mils. Okay? As a side note, Bakelite is no longer used in the PCB industry. It's been long since phased out. You don't see Bakelite generally in products anymore as well. As I mentioned earlier on, there's a lot better products out there and plastics that have substituted in for Bakelite. The biggest problem with Bakelite is that actually a good component of it, if you look at the material makeup of it, is formaldehyde. And as you probably know, formaldehyde is considered right now to be a possibly known carcinogen. So no company really wants to play with that stuff at this point. All right, and let me just show you something here very quickly. If I go to the top here, and I thought this was kind of neat, when they set this up here, you'll notice that the board thicknesses over here, when they set these things up here, was about approximately 63. So the examples they give over here tries to keep to the original standard or concept. And again, do you have to do it at 63 mils? No, you don't. However, again, depending on the board size, you want to work with your fabricator to make sure that you're not building something so thin that the thing's just going to fall apart. All right. What else we got over here? Good stuff. Classic core prepreg materials. The reason I say classic over here is they may be using other materials other than this, but the classic core and prepreg materials, I say the vast majority of them out there, is woven glass, and that's what you're looking at. It's woven glass, fiber glass. Reinforcement, and what they mean by reinforcement is something that can hold these things together, along with a resin. Okay? So you're basically looking at the woven glass, and there's different types of weave. So this one has a lot of gap to it, and this one's a very tight gap to it. And here's a wonderful cross section of it, so you can take a look at how it looks. But that's what they're doing. They're using woven glass along with glue or resin, which I basically, again, treat it like a glue. And so when it heats up, the resin is going to melt, and it's going to allow you to connect cores together or foil together. As a matter of, yeah, and I'll show you here something in another slide here in just a moment to that effect. I also want to talk about this thing called the concept of curing, because we don't see this very often as electrical engineers or electrical designers, but it's used in several other industries. This concept of being cured is taking, if you look at the definition, I broke it up down here, and it's the best way to look at it. It's the toughening or hardening of a polymer material. So what's a polymer material? It's something that's a very long chain of atoms. Okay? It's a very long, stretchy chain of atoms. And what you're doing is you're cross-linking of the polymer chains, and it's brought about by electron beam heat or chemical additive. So where we see this quite often, number one, is in the dental industry. So here's an example over here. So on the top, you see that they've actually added in some type of polymer, and now they're applying a light to it so that they can harden it. Or if you're familiar, if your kids have ever had an orthodontist or they've had braces, applied by an orthodontist, they'll normally place on the bracket, and then once they get the approval, then they'll shine a light on that, and it will harden the material so that it will stick to the tooth or the enamel of the tooth. Okay? The other one I like over here, I got a kick out of this one. This is an example of what you call off-label. So this is somebody who basically did kind of one of those do-it-yourself. They were using this for their for the making of their printed circuit boards. I think they were using it for probably the lithography aspect of it. It's a UV light thing, and it's primarily actually used so that those people who have their nails painted, they would stick their fingers in there, and then the UV light would harden whatever material that they put on the fingernails. Okay, so that's what I got a kick out of this. So even though the salon industry was using this, someone found a great way to use this in the PCB industry. So want to put that out there for your humor. Anyways, for material, this is one I wanted to show you over here. So here's a great example of Prepreg, and you see that it's kind of mushy. You can wave it around. It's not rigid or stiff. And then what you see happening over here is they're actually doing the layer stack up. So if you look just below that, you see that there's the copper that's already been etched out on this prior layer. That's probably a core material that's being placed there, and now they're placing the Prepreg on top of this, and then they'll probably put another core material, or if this is the top of it, they'll put the copper foil on that next. Okay, and there's a YouTube video here, but I want to capture this so you got a feel for what this looks like. What you can't see here very well in this picture is that there's actually 4 posts. So they call this a laminate book, and in order to register these things, they've got 4 posts over here. So when they place these down, each one of these layers has these holes in here so that they can make sure that the register is done properly. So what's going to happen with this is they're going to put it into a piece of equipment that's going to apply both heat and pressure to it, and obviously that's going to melt this here, and it's going to laminate everything together. All right. So if we take a look at this, basically the resin is going to flow into any gaps that are in the planes because material has been removed from the chemical etchings. It's going to go around the traces. It's going to even squeeze out the laminate book. So they have to be a little careful. If they squeeze this too hard, you can actually squeeze out more laminate than you really wanted to. But what happens here, probably not laminate, but Prepreg, the result of it is that the traces actually become much closer to your plane. And the dielectric didn't change. It's just that now your distance from the plane to your signal is a lot shorter, and so it actually reduces the impedance as well. That may be a good thing. That may not be a good thing. It depends on how they control those things and what you gave them initially to work with. Okay, so there it is. That's the apparent thickness, which you see here, and the actual thickness after the lamination is done. So again, it goes back to this, what I was talking about. Let me drag this back over here. This is what I was talking about earlier on, is that you can play with these numbers all you want, but when they put this thing through its process and then they laminate it over here, these numbers, these dielectric thicknesses are going to change, and as a result, that's going to impact your characteristic impedances. All right, so let's see. Let's talk about the process itself. What is the process? We talked about the different materials. What's the process? So the key thing you got to remember about this process is that you work inside out, not top to bottom, not bottom up. You work inside out. So you work from the center outward. Okay. So let's talk about a 6-layer board for a moment. What you see over here are layers 2 and 3. So they're being treated like core material, along with 4 and 5. So what they would do before anything else is that they would etch out layers 2 and 3. And they put the etch resist on top of it based on what you drew in your PCB layout tool. They put the etch resist on there. They would put this through a chemical bath. They would etch this out. Same thing for layer 3. You do the same thing for layer 4 and layer 5. Now, after we've done that over here, we've got these, but we've got to attach them together. So what you've got to do is you've got to add in layers of prepreg. And I know this looks almost a little overwhelming, but keep in mind that what you see over here where my cursor is circling is the original core that we just talked about on the last page, and here's 4 and 5. So what we're inserting in here are prepregs on above, middle, and below here between those cores. And then also on top of here, we will put down a copper foil on the top and the bottom. So this is kind of the normal fabrication process that you would normally see. Then this would all be laminated together, and then at this point, you would actually etch out the top layer and the bottom layer. Now, if you are doing some type of blind or buried via, you would have some steps in between to make that happen, obviously, because once this has all been laminated together, you can't do a blind or buried via. You would have to do a through-hole via at that point. So it depends on how you set up those, and we'll talk about vias here in just a moment. All right, so another way to look at what we just saw over here, because if this is just a little overwhelming and you're having a hard time getting your eyes around it, here's another way to look at it. Signal, prepreg, plane. Basically what you've got is copper dielectric all the way through. And again, some of it was core, some of it was prepreg, and in the end it doesn't really matter because when you're done laminating it, it's all hardened. So, you know, the prepreg's now hardened, the core wasn't really impacted by it because it was already hardened, and so on and so forth. Okay. Before I show something else over here, what I wanted to do is show you a high-speed stack-up, and then I'll show you here. I'll actually build this over here in the other tool together. Now, when you're dealing with high-speed stack-ups, as I mentioned earlier on, you've got to have a plane for your signal layers. There has to be a reference to that because of what they call the current loops. And in high-speed design, when the signal is propagating from point A to point B, there is a return path that's necessary, and that's why you got to provide that plane. And we talked about this in several other webinars in the past. If you're interested in that, contact us and we can go into greater detail about it. But hopefully that makes sense to you here. So when you're dealing with high-speed design, you want to do things really in what they'll call triples and doubles. And you want them always to be an even number. So in the industry, you normally do not make like a 7-layer or 5-layer board. You usually work in pairs, and you always want to try to keep the symmetry. You're always worried about warpages. You're also always worried about twisting as well. So symmetry helps with avoiding those type of issues in the fabrication process. So if you look at this 8-layer stack up over here, we have 3 signals here. Well, really 2 signal planes and a copper plane. We also have 2 signal planes, and I shouldn't call them signal planes, signal layers, along with the plane over here on the bottom. So they are symmetrical to each other, mirrored but symmetrical. And then, of course, we have these 2 in the middle here, primarily to not only help our signals on layer 3 and layer 6, but really to separate the signal activity from the top with the signal activity on the bottom. Normally in high-speed design, you want to separate those activities together. So whatever happening on the top, you keep towards the top. Whatever's happening on the bottom stays on the bottom. Now, granted, there usually has to be some type of communication between the top and the bottom, and so you'll have a through hole for that, but you really want to minimize that as much as possible so that you can avoid a lot of the talk and try to keep those current loops as close together as possible. Now, in the tool itself, and I do want to walk through this a little bit slower because I've shown you some examples, and sometimes it's nice to see these things kind of come together here a little bit slower. So I'm going to start a new layer over here, and I'm going to right-click here, and I'm going to also just throw in, it doesn't matter if I sort above or below. I'm going to do a core material, and now it will matter because I'm going to sort above over here the core, or pardon me, a plane, and I'm also going to sort on the bottom side of this, so sort below another plane. So now you can see, again, working middle on out, what I've got over here is I've got my core with the plane on the top and a plane on the bottom. And what I'm going to do here is I'm just going to build the top part of it next. One thing you may have noticed here is I didn't put a prepreg here and bottom here. I just want to show that concept of the triple and the double. So what I'm going to do is I'm going to right-click, sort above here, and put my prepreg in. Now, again, there is another core here. So let's put that core in, just look at that for a moment. So we're going to put the core in, and of course we wouldn't have 2 dielectrics next to each other. The question is, what are we going to put here? Are we going to put a plane here, signal down here, or vice versa? Obviously, this is the best situation here. So we want the core to be on the bottom so it can take advantage of the 2 planes that ultimately are going to end up here, the plane that already exists on 4 and the plane that will exist on 2. Okay, so if I go here and I sort below, I'll put a signal down here, and if I sort above here, I can put the plane on here. And then, of course, lastly, we're going to deal with the copper foil and the prepreg. So on top of this conductive, on the above, we'll do the prepreg, And on the top here, above here, we'll also do a signal. And we also have, and we haven't talked much about it, and we just unfortunately don't have a lot of time to talk about it, the solder mask. And of course, the solder mask is there really to protect the copper, because if the copper is exposed to air, it has a tendency to react with it, and it will degrade the overall circuit. So it's really a protectant for the copper itself. Okay, so there we go. We've just kind of built up pretty much half the stack up. I'm going to cheat a little bit over here due to time, so I'm going to cut this one out, and I'm going to use a feature here. It's called a mirror stack up. So if I click on this, it'll build the bottom part of it. And so now I've got my stack up completed. But hopefully you see the idea here. We're always going signal, copper, signal, copper. Some of it's going to be copper. Some of it's, some of it's going to be core. Some of it's going to be prepreg. And of course, we always want to keep the symmetry. Okay. Let's move this out here for just a moment and jump on over to our vias. So there's a number of different vias, and you can spend a lot of time investigating these things. There are three basic types, obviously, the through hole, the blind via, which means it starts either on the top or the bottom, but always ends in a mid layer. And then you have a buried via as well. Okay, and the buried via basically never sees the light of day. There's additional vias out there. There's one that's now called the micro via. It's been out for a while, but it's becoming more cost effective. It's a via that's a less than 150 microns. It's done by laser, and it's used for one-layer connectivity. But what the slick part about this is that if you want to actually stack these one on top of each other, you can actually do it. I've seen a couple of pictures of it. But again, just be careful of the cost. The older methods of blind, buried, and through-hole vias are the most cost-effective. You also might see vias, micro vias using what's called via and pad. We talked about this quite a bit during our layout considerations DFM series on this. Be careful about vias and pads. You could possibly use micro vias, but now you're confining yourself primarily to one layer unless you do a stack up accordingly. If it's a larger via that you put in the pad, you have to fill it in afterwards. So fabrication doesn't have an issue with it. It's assembly that's going to have a problem with it. So be really careful about using the via and the pad, or understand what you're getting yourself into and determine if that's the cost that you want to do. The big thing with the via and the pad is that you don't have to dog bone it, meaning that you don't have to take a piece of trace, jump out from the pad, and then drop a via hole in it. So there's a room consideration, especially if you're in a very dense area, but you pay the cost in assembly. One of the things that we have to understand about vias is the concept called the aspect ratio. And obviously we want to have small holes, but we have to have holes that are realistic that we can actually drill. So it's a ratio of board thickness to hole diameter. And so yet another reason that we need to know the board thickness. Okay, so that board thickness seems to kind of come back again and again and again. So the reason we need to know this is because of the fact that, number one, we have to worry about the initial hit of the drill. If we're using a material where it's a little bit harder for it to hit on target, it may be off, and in certain classes, that may not be acceptable. Okay, so it depends on the class that you're trying to build for, where if you're not directly on the hole that you're trying to drill for that via, they may not accept it, or there's going to be a lot of high fallout from that. The angle of the drill in which it goes in, the thicker that this board is, there's going to be an angle that's going to start happening with it. I mean, these things are tiny. I've really widened or made this much bigger than what it looks like, but these are very small. There's a little bit of flex to them, and if they go in at an angle, well, in a bigger board, that could be a problem, or maybe it hits the first 3 layers, but the next 5 layers it doesn't register correctly, or pardon me, it doesn't hit the pad because the angle is so far off. And of course, the registration of the layers as well. So there's always a little bit of slop between the registration of the layers, and of course, the larger number of layers over there, the more opportunities there are for misses. The common ratio is 8 to 1. Okay, so any company that, pretty much any fabricator out there can do anything 8 to 1 or less. Okay, for the ratio here of the board thickness to the hole diameter. From 8 to 1 up to about 12 to 1, a lot of companies can do it. However, you're going to pay a higher cost for it. And anything from 12 to 1 and beyond that, you're going to pay top dollar for it. Okay, so it all depends on the type of board you're building. If it's a Happy Meal toy, I don't recommend you go to 50 to 1, right? Maybe some companies can do that, but that'd be a very expensive Happy Meal toy, right? So be very careful about the vias that you're using. Don't just pull them out willy-nilly. And again, your fabricator will tell you this based on the materials that you're using and the proposed stack-up that you have, and they can tell you this information. The other thing I find, too, is that let's say that you're not even worried about the hole size. You're just going to put big honking holes in there, and you're not worried about it. What I've seen with a lot of tools is that you can put these holes anywhere you want. All right, you can start and stop on any layer you want. So here's an example of one that might kind of work if you've got a bunch of stacked vias. Here's one that just won't work at all because it's impossible to do. Okay, and I've seen this happen because tools will allow you to do these things, and then you hand them off to the fabricator and said, sorry, not going to happen, and you turn up your routing, and it's a tragedy at that point. So be really careful about how you do these. The last example I'm going to give you is a real one, and going back to this one that we just made here, is just one strategy that you can use, one of many. It's not the only one, but one of many. And again, in a high-speed environment, for example, you're going to obviously have signals on the top, and you're going to have signals on the bottom. But what you want to do is kind of keep those things on the top to the top, and you can do that by saying, okay, look, I can do some routing on the top layer, but I need a little bit of help because I got a lot of components in the way. So I want to be able to drop things from layer 1 down to layer 3, and then possibly bring it back up again. Okay? And in a similar fashion, whatever's going on layer 8, I may need the assistance of layer 6. And of course, I'll have a through hole, so if I do need to send things through, I'll send them through from layer 1 down to layer 8. So what we're dealing with over here is an example of buried vias. So I'm going to throw a couple of those in here right now. So to do that, I'm going to put in layer 1 to layer 3. Okay. And I'm also going to mirror it because it's smart enough to know that if I'm going to do this from 1 to 3, it's also want to do it from 8 to 6. Pardon me. And so when I do this, you can see now I've got two buried, I'm probably not buried, blind vias. Okay. Again, they start from the top and they end midstream. And this over here would be an effective way to do it. Are there other things you can do like back drill? Are there other things that you can do like buried? Are there other things that you can do such vias? You can, but again, talk to your fabricator, because if you come up with some wild scheme and you try to implement it and then go to them, it could be a very expensive endeavor if they can even do it. Okay. So that's what we've got over here. So at this point, I've got a couple more minutes left in this hour. I just want to throw some information out at you before I turn over the Q&A section to my colleague, Jeff Condit. So Barry Olney is the one who created this tool, as I mentioned earlier on. Here's his information here. He's written a number of articles on this. Again, I also mentioned that earlier. And I asked him, he said, hey, Barry, can you send me the examples that would be very apropos to what you've done, that would be apropos to this particular webinar? And he said, sure, and he certainly did. He actually went through this yesterday with us over here. Barry's out in Australia, and so he's hopefully sound asleep and not worrying about this webinar at this point. But he gives his regards, and we're very thankful for the information he provided for this webinar.